In this video, we will talk about repeated measures ANOVA. Repeated measures ANOVA can be thought of in its basic form as similar to the paired samples t-test, in that measurements are related in a systematic way, except that in the repeated measures ANOVA, you aren't limited to one factor or to two levels. For example, data for a repeated measures ANOVA may be multiple time points of testing per person. You may have data for the same person, say the same child, measured across different years. Or you may have a set of comparable tests administered to the same person, and you may want to compare performance on these different tests. As with the factorial ANOVA, the strategy to analyze these data is to partition the total sum of squares so that we can compare ratios of mean squares. So we approach the problem from the point of view of accounting for variability in the observed data. The difference from the factorial ANOVA is that we're not interested in the total sum of squares anymore. Rather, we're interested in the variability within each person. We're not interested in differences between participants, between different children. We're interested in the differences between time points or between tests for individual persons on average. So the relevant sum of squares that we want to partition and to consider ratios of sum of squares within it is not the total sum of squares, but only the part of the total sum of squares that concerns differences within the participants. So the residual, what is left over after something is accounted for by our factor, is not the total residual, but the residual left over from the within sum of squares, the sum of squares of the differences from each person's own mean. So each person's data points are used to calculate the deviation from each person's own mean performance across time points or across tests. And that forms the within sum of squares that we partition to that part that is accounted for by the factor and that part that is left over as a residual. I'm not going to demonstrate this calculation at all. It gets fairly complicated quickly, and there is no point in getting it done because we never actually do it manually anymore. The programs do it for us. As long as you have the basic understanding that we're after partitioning sums of squares, and you understand that what is relevant now is the variability within participants, then you're all set to go on and read and interpret ANOVA tables. We'll use an example to illustrate how this difference in relevant residuals plays out in how the F ratios are calculated. For this example, we will use longitudinal data, so 169 children who are measured in grades 2, 3, and 4. It's the same children who are administered the same test of reading comprehension again every year. There are 86 girls and 83 boys. So our dependent variable is the raw score on a reading comprehension test, the number of questions answered correctly out of 18 questions total. And our independent variables are sex, which is between the participants, between subjects, with two levels, boys and girls, and grade. That is a within subjects factor, or the repeated measure, in other words. And this factor, this variable has three levels: grade 2, grade 3, and grade 4. We will start with the simple case of only considering the within participants factor, the repeated measure here. So we start by ignoring sex and just looking at the effect of grade longitudinally. Here is the box plot and the associated analysis for this group of children. The F ratio that you see here is calculated by dividing the mean square for grade with the mean square for the within residual. This is not the total, the residual from the total sums of squares. This is the leftover from the within sums of squares, the differences of the data points from the child's own mean across grades. This effect is statistically significant. The p-value is very small. This is a very large F ratio. And therefore, we can reject the null hypothesis that there is no difference in the means of different grades for these children. This means that individual children on average increased their own reading comprehension score across grades, which does make a lot of sense. The effect size for this comparison is a partial effect size, a partial eta square, because we aren't dividing over the total sum of squares. We are dividing the sum of squares for the factor over the sum of this sum of squares and the residual. So this is a partial eta square, and that's 0.36. If we want to calculate the proportion of the total variability accounted for by this repeated measures factor, then we would have to divide by the total sum of squares, and that would be about 15%, actually 0.155. Note that the number of degrees of freedom here is 336, and that's twice the number 168. There are 169 children here. So why twice that number? Why twice 168? Twice because there are two relevant differences in here. Remember that the repeated measures ANOVA is analogous to the paired samples t-test. And for the paired samples t-test, the relevant sample size was the number of participants, not the number of data points, because each participant contributes one difference score, not two scores. Remember, in the paired samples t-test, we subtracted the two scores, created one difference score, and then we used that in a one sample t-test actually. So the relevant metric there was the difference, not the scores themselves. In a related fashion here, the relevant metric for the residual is not the three different levels of the factor, but the fact that these are composed of two differences, which correspond to the changes between two pairs of groups, and only two, because if you know the two differences, the third difference is already defined, so it's constrained. So there's two relevant differences here for the number of children. If you have taken out the degrees of freedom associated with the group means, so that leaves you with 336 degrees of freedom for the within residual sum of squares here. So that was a repeated measures analysis of variance with a single repeated measures factor with three levels. What if we have more than one independent variable? Let us consider the case where we have this repeated measures factor as well as a between groups factor, so sex and grade. This is the box plot for the data broken down by sex and grade. Remember that the different grades correspond to the same children. They're longitudinal measures. It looks like there is no difference between the sexes, although the first quartile of the boys is consistently below the first quartile of the girls. And in grade 3, the median for the boys is also lower than the median for the girls. These are unlikely to be statistically significant, but we can't know before we check. This is the corresponding line plot, which shows indeed a slight advantage for the girls, which may or may not be statistically significant. And we also see the lines that join the grades. So we see clear differences between grades for boys and for girls. And of course, when you have two variables in an analysis of variance, usually the interesting question concerns the interaction. So is the effect of one variable different across levels of the other variable? Here, is the difference between sexes the same across grades? Or is the difference between grades the same for boys and girls? That's like asking, do girls and boys grow equally in reading comprehension across these three grades? Remember, these two questions are equivalent. To ask whether the effect of grade is affected by sex is the same as asking whether the effect of sex is affected by grade. And they're both visible in this graph by checking the slope of the lines. So this line and this line show the relative change for boys and girls. If girls grow as much as boys between the second and third grade, as they seem to do here, these lines will be approximately parallel. If girls and boys grow up to approximately the same degree between grades 3 and 4, these lines will be approximately parallel. So parallel lines on this line plot indicate no interaction. There does not seem to be a statistically significant interaction based on this line plot. If, in contrast, our data looked like this, then we would see that the slope of this line is greater than the slope of this line. This graph shows that girls increase their scores more between grades 2 and 3 than boys do. This is a smaller slope. The line doesn't grow as fast as this one. And there is probably no difference between these slopes, which is hard to tell in the graph. But overall, if this were our situation, then we would expect to see an interaction between the two variables. However, our actual data are these, and these do not indicate that we should expect a statistically significant interaction. Let's see what the actual analysis says. When you have both repeated measures and between participants or grouping factors, then what you have is called a mixed design ANOVA, or a mixed ANOVA for short. And that's defined as an analysis of variance with two or more independent variables, at least one of which is a grouping variable and one of which or more is a repeated measure. So when you have both groupings and repeated measures, then you have mixed ANOVA. Grouping variables are called between participants or between subjects, and repeated measures are also called within participants or within subjects. The tricky part about a mixed design ANOVA is that different kinds of variables, the effects of different kinds of variables, are gauged against the corresponding residuals. So the residual sum of squares that is relevant for a grouping variable is not the same as the residual sum of squares that is relevant for a repeated measure, because the residual for the grouping variable is what's left over from the total sum of squares, but the residual for a repeated measure is what's left over from the within sum of squares. Now, don't despair, because you never have to figure this out yourself. the analysis program will construct the appropriate table for you and group things accordingly. However, it is important to understand where this comes from and why, so you can interpret those tables. I'm not going to show you any calculations, just going straight to the Anova table as you will see it reported in an analysis program, and starting with the main effects. Remember, the main effects are the average effects of the factors. So the effects of each factor on average over all levels of all the other factors. Here is the Anova table. And see, in this table, we have two different groups or strata, as they're called, because we are interested in the within section and the between section separately. So here we have the residual, the leftover from the within participant sum of squares, and we also have the residual from the total sum of squares. And if you add all these sums of squares, you will get the total sum of squares for your data, for all your observations. So that's always true. The Anova table presents a list of sum of squares partitioned into effects of factors, effects of interactions, and residuals at the different strata. So what's left over within and what's left over for the total. The main effects concern the effects of the factors individually on average. So the main effect of sex on average across all grades is given by dividing the mean square for sex over the mean square for the total residual sum of squares. And that's an F ratio of 2.65, a p-value not statistically significant. We cannot reject the null hypothesis that boys and girls have equal scores on this comprehension test. So no statistically significant difference by sex. The main effect of grade is seen by dividing the mean square for grade associated with the sum of squares for the means by grade within participants, and divide this one over what's left over from the within participant sum of squares. So the variability within children, the differences of scores from the children's own means, that variability that is left over after you've accounted for the fact that children are tested across 3 grades. And this divided by this is a very large number. It's 93.3. And of course, the p-value is very low. We reject the null hypothesis that children's means are the same across grades. And we conclude that there are differences between grades on average for these children, as they're followed up longitudinally. Turning to the interaction, so asking whether the effect of sex differs across grades or the effect of grades differs across boys and girls, we divide the appropriate mean square with the within residual, because grade is a repeated measure. And we get a very small F ratio and a very large p-value. So there is absolutely no hint of an interaction here. This is not statistically significant. We do not reject the null hypothesis that the effects of grade are the same for girls and boys. Turning to the effect size, we can calculate an eta squared for each effect by dividing the corresponding sum of squares over the total sum of squares. This is the sum of all of these sums of squares. It's the total sum of squares for this data set. And for sex, this is a very small, it's about 1%, and it's not statistically significant, as we said. For grade, we divide the sum of squares again by the total to get eta squared, and that's 15.5% of the variability in the data that's accounted for by grade. That's the proportion of variability. Remember, this is a proportion of the total. So the rest, the remaining 85% is not all noise. Actually, a large part of it is differences between children. The effect size for the interaction is really tiny, and it should be reported as less than 0.001. These were the proportions of variability, so proportions of the sum of squares that were accounted for by each factor and the interaction in the data. So they were the total eta squares. What about the partial effects? We can calculate partial eta squares that concern only the part of variability in the data that is not accounted by anything else. So if we divide the sum of squares for the sex factor by the total of this sum of squares and its corresponding residual, this excludes sums of squares associated with anything else. And so this partial eta square is 0.016. The partial eta square for grade calculated in the same way, except now the corresponding residual is this one. So excluding variability that is relevant to other things, the partial eta square for grade, which is a repeated measure, and therefore it's the within residual that's relevant, that's a partial eta square of 0.358. And the partial eta square for the interaction is again tiny. So that's how you interpret and report a mixed design ANOVA result. Before you go on to actually interpret and report, however, you should have checked that your analysis meets the assumptions that underlie these calculations. The first assumption is the independence, to the extent that you're not talking about repeated measures. So whatever isn't a systematically manipulated repeated measure should be independent. The dependence should be only by design and should correspond to a repeated measure. Otherwise, the data should not be dependent on one another in any way. The second assumption is normality, and that's assessed in the usual way when we look at our data with the Shapiro-Wilk test or other tests of normality. If there are between participant factors, those factors must fulfill the homogeneity of variance assumption across their groups, across their levels. And that's tested with the Levine test, as we have seen in the video on factorial ANOVA. In addition, when we have a repeated measures factor, the assumption of sphericity must hold. The assumption of sphericity is conceptually the same as homogeneity of variance, except that sphericity doesn't concern equality across groups or across levels, but concerns the variance of differences between levels. So if you have a repeated measure with only two levels of the kind that you could analyze using a paired samples t-test, then you only have one difference. Two levels of a repeated measure are one difference. So there is no issue with sphericity if you only have one difference. If you have three or more levels, that means you have two or more independent differences, and those have to be checked for the sphericity assumption. So those differences should be distributed equally, should have the same standard deviation. There is a specific test to assess that. And fortunately, if the sphericity assumption is violated, then you can apply a correction. The analysis produces a correction factor, and instead of reporting the finding of the plain uncorrected repeated measures analysis, you can report the line that corresponds to the correction factor. In other words, the sphericity violation is not so serious from a practical point of view because it can be worked around using a correction that is also reported in the analysis. So you're not in trouble with having to find different approaches to analyze your data.